Thank you very much for coming, and I hope that I don't stand in the way of the picture. What I want to talk to you about today is about radiocarbon dating. So that's a method of measuring the age of objects, and I'm going to try to apply this to various kinds of artworks. And I hope you can hear me at the back because I usually don't talk loudly enough. And so I've been working in Debrecen since last September at Atomkey. I'm working with some colleagues there who are also working on radiocarbon dating. And so I want to try and show you the connection between, so America, in this case, Arizona, and Debrecen. So most of you are not science students, so I think that at some time you had some introduction to the idea of the atom. So we have carbon atoms that's making up most of the people in this room. I hope all of them. And there are three different atoms of carbon. The first one is carbon-12. This is the main one. This is a stable atom of carbon and has 6 protons and 6 neutrons. And we can also have one extra neutron, and we call this carbon-13. This is also stable and is about 1% of the carbon everywhere in the world. And then a very small amount is carbon-14, is about 1 part in a trillion. So 1 part in what I would say 10 to the 12 in a scientific language. That means 1 with 12 zeros after it. And so this is a very small amount of carbon, of the natural carbon. And this isotope, that means a form of the atom, is radioactive. This means that it decays with a known time, which we call the half-life. I'll talk about that in a moment. And we can use this as a kind of clock. So everybody in this room is in some equilibrium with the atmosphere because we are what we eat, okay, basically. And when we're removed from this system, the carbon-14 will decay from the original level, and then if we measure that amount of carbon-14, we can determine the age of the material. So if we find some bones in the ground, we can estimate the age from how much carbon-14 is in the sample. And so I have a little video here. Oh, I have some aid, I hope. So the idea is that the carbon-14 decays with time. It has a half-life of this number, 5,730 years. This means that 1/2 of the carbon-14 decays in this time, 5,700 years. If we wait another 5,700 years, 1/2 of the remaining amount decays. So then we have 1/4 left. And it should look like this. So this is a plot of time, number of half-lives versus how much is left. After 1 half-life, 50% is left. After 2 half-lives, 25% is left, and so on. Now, some people think this is very mysterious, but it's not mysterious at all. It's just statistics. And if you apply this in the opposite direction, actually, if you want to calculate how much interest you have in your bank account, you can use the same kind of equation to determine how much is there or not there. But the idea is that basically we understand how carbon-14 depends on time, and we can use it to measure the age of different objects. That's really all you need to know. And this is what we would call an exponential decay. So that's all the really technical part of this talk. I have a couple of pictures of equipment because when you work in the physics institute, you always have to show a picture of the equipment because everybody likes that. So in the early days of carbon-14, this is developed after the Second World War. There's a famous Professor Libby he was at the University of Chicago, who developed this method. And what I like to tell people is that actually the graduate student did the work and the professor got the credit. This is how it works in the academic world. So so you have to get beyond being a graduate student, I guess. So in the early days, we measured the decay by counting the decay of the carbon-14 atoms. And later we learned that it's easier just to count the atoms themselves before they decay. And then, first of all, it's easier. And the only problem is we need a much bigger machine. So I'll show you a picture of a machine in a moment. So this is a complicated picture of how this works. So this is for the physicists in the room, which are probably not very many. So basically we have some nuclear reactions in the atmosphere that are producing the carbon-14, and the carbon-14 is incorporated into the biosphere. That means trees, animals, people. And then when you are removed from this system, so you die, then this level will decay. So don't worry about this picture. I have a much easier picture, which is here. And so this shows you the same thing, except now I use a picture from Arizona. So this is not Hungary, okay? It has a mountain. Also some cactus. So this is the same idea. We produce the carbon-14 in the atmosphere because the cosmic rays from the space are hitting the atmosphere. And this is incorporated into the biosphere, which is this nice plant here, which is not growing in Debrecen, maybe in the botanical garden. But this is called a saguaro cactus. It's a very famous plant in my region of Arizona. And we love this plant very much. And sometimes it even has flowers. So the carbon-14 is incorporated into these plants. Animals eat the plants, and people eat the animals or the plants. So that's how the carbon-14 gets into you. And so everybody in this room has the same amount of carbon-14 right now. Doesn't matter who you are. And this is the starting point of this calculation. So this is a slightly other picture, different picture. It shows you the same idea, but we also know that besides the biosphere, there's also other large bodies of carbon on the Earth, such as the ocean. And there the level is a little bit different. But for my talk, we won't worry about this. In recent times, we have another source of carbon-14, which is produced by nuclear testing. So since about 1950, the carbon-14 in the atmosphere is increased by mostly by nuclear weapons testing in the atmosphere. And this peaked in 1963. In 1963, the US, Britain, and Russia signed an atomic weapons treaty where they agreed not to do this anymore. And so since that time, this level has been going down. And so now it's close to what it was before. There were some other small tests by other countries, but not so important. And so this signal can be used to tell if something is made in the last 50 or 60 years. So this is a very important signal. Okay, the reason is not very good because we don't like nuclear weapons, but there is one result that we can use, this signal to tell if something was made recently or not. So I'll come back to this. So I mentioned I have to show a picture of the equipment. So this is one particular large machine for measuring carbon-14. So if you know anything you know about accelerators, you know this is some kind of accelerator. I won't try to explain this to this group, but basically in order to separate the atoms, we need a very large machine. But with the technology developing at the moment, these machines now become smaller. I'll show you one picture of a machine in Debrecen, which is really quite small. So this is a large machine in Tucson, Arizona, the University of Arizona. And you can see this is a very big machine. So this was what we believed until very recently that we needed to do carbon-14 measurements. We need a very big machine because it's a very small number of samples. And in some kind of rule, I guess, that in physics, if you want to measure something very small, you need a very big machine. That's what everybody thinks. But actually, this is not true because this is a much smaller machine. This is actually in Atomki in Debrecen, so it's 2 kilometers from here or less. And this machine is, you see the scale of my colleague here. then this machine is much smaller to a kind of equipment you can put in a small room, smaller than this one, and you can still measure carbon-14. So this is about the third machine of this design which has been installed, and it's here in Debrecen, so that's something to be proud of. And so what I want to do is to give you some examples of how we use this. I start with some controversial examples, and then I go to not controversial examples. So I mentioned that this guy, William Libby, Professor Libby, he got the Nobel Prize for this method in 1960. He didn't have an accelerator, he just counted the decay of the atoms. And what he did was he took a whole lot of material that he knew the age of. He got these from a museum in Chicago. And he measured the carbon-14 in these different samples. And then he plotted them, and he showed that they sort of plot on this exponential decay curve that I mentioned before. And he also noticed that actually it didn't quite fit. So you can see that some of the points don't quite fit on the line, and this is because the production of carbon-14 in the atmosphere is not constant. It varies with time, so we actually have to calibrate the age by looking at other materials of which we know the age. And usually we do this by looking at tree rings. So we have an archive of tree rings going back 12,700 years, which is continuous. That means we have a tree ring for every year. And beyond that time, we have other ways of calibrating the timescale by cross-referencing it to other methods. But this is a picture of very old trees which are growing in the White Mountains of California. These are mountains basically on the border between Nevada and California. And these were some of the first trees used to establish this chronology. So that's the hard part. The easy part is how can we use this? And there are very many interesting materials, artworks, artifacts, other objects, which we can date using carbon-14 because the material at some time was part of an animal or a plant, and when the plant died or the animal died, the carbon-14 in that material started to decay. So we have this case is a scroll. It's parchment. That means it's the skin of a sheep or a lamb. And this one is silk. It's a textile. This one is a painting on a wall, a kind of fresco. And this one is obviously a statue. So there are all these kinds of materials that we can potentially date. And so I start with one question. So I need somebody to tell me the answer to this question. So you see these two objects here. Which one is the old one? Anybody knows? Guess? Nobody wants to guess? Okay. This one looks older, right? But it's not. This one is 2,000 years old, and this one is very recent. And so the problem in the art world is that people try to make copies of older objects, and they can also know how to make them look old. They stick them in the ground, they bury them in the river, they put them in the Hotabadge or somewhere for a while, and then it gets older. So it looks like it's older, but it actually isn't. So this is a question that we're asking all the time when we see an old object. So in my lab, people come to the lab, they say, I have a painting of Leonardo. And we say, yes, but Leonardo only made 28 paintings. He didn't make very many paintings. His students made lots of paintings, but not Leonardo. But somebody finds a painting, they always want it to be something very valuable. And sometimes it's just a copy, a later copy, which may look just as good, but it's somehow not as valuable. So there's one example. And at the end, I come back to some other stuff that we do that's not related to art, just to give you an idea of why science is interesting. So this is one object that most people know what this is. This is called the Shroud of Turin. This is the most famous object ever dated by radiocarbon and the most controversial. And I show this because probably in a few weeks this will be on the television every day, because at Easter time this is a very popular topic. So most people, when they talk about this object, believe that there is an image on this object. And you can see that this is actually extremely faint. It's only the pictures that you see of this object are enhanced photographically, and that's why you see the images that you see clearly. So in our laboratory and several others, this is done a long time ago, 25 years ago, samples were taken for dating of this object. And so the object turns out to be medieval in radiocarbon age. And these are some just pictures of the samples. I don't want to spend a lot of time on this, but I'll show you that. So this is our calibration curve that I discussed. We constructed a calibration curve from looking at how much carbon-14 there is of tree rings of different age. And you can see that the age comes out to be sometime in the 14th century, 1300 and something. So this is the radiocarbon age of this object. So if you're a scientist, you say, this is what I measured. The problem is that there are many people who believe that this result is incorrect. They're not scientists, but they believe it to be incorrect because they believe in this object. So this shows something about the limitations of science. So you can certainly measure lots of things, but you can't necessarily convince people that your result is correct. So this is just, I don't say this object is real or not. I just say that we measured the age, and so then that's the observation that is made by the scientist. So the scientist always operates by looking at observation or by looking at a theory which is then applied to observations. So if you don't want to accept the science at that point, which is what in this particular case, then obviously you have a different conclusion. But the scientist is still operating from the same principles of observation or theory applied to an observation, or an observation which follows from the theory. So that's something to bear in mind. So this is a mindset that scientists have, which may be different from other people sometimes. And sometimes this raises misunderstandings. So let me move to some other objects which are not controversial. So you notice that a few of these have some religious connection. This is just kind of because they're very interesting objects. So this is a scroll. This is it's made on parchment, which means the skin of usually sheep. And this object is over 2,000 years old. It's a copy of the book of Isaiah, and it's on display in Jerusalem in the museum. And many people tried to date these objects by radiocarbon, and they all turned out to be about 2,200 to 2,000 years old. And so there is no controversy because everybody says, of course, we knew these are 2,000 years old. What's the problem? So, so this is kind of opposite example from the one I just showed. And this is a very interesting object. You can see that the edges are quite damaged by time, but we can still remove some material to do dating. And I think I have a few pictures of what these objects are, just for interest. So these objects, most of them were discovered in the late 1940s. Some of them were discovered later, and most of them are associated with possible archaeological settlements in the Dead Sea region. That is, it's basically in the West Bank, so it's between Israel and Jordan. This part is under Israeli control at the moment, at least. And since the 1940s, many people have tried to study these objects because they want to read these books. Many of them are copies of books of the Bible, which are in the Hebrew text identical to the current text. And other ones are commentaries on these books, so they tell you something about how these people lived and how they thought. And they had very, I would say, extreme views, let me put it that way. And then the third kind of documents are just business documents. So the sale of a property, invoice, something like that. The same kind of business documents we would see today, except they will be written on papyrus or parchment. So papyrus means something made from plant material as opposed to animal material. So I just have a few pictures about these objects because it's kind of a discourse from talking about science. So I like to show this picture because this shows the people involved in finding these objects, which you may imagine are not as reliable as they sound. So the story is that some small boys found these objects in a cave. So this sounds like a great story, right? Some small boys are playing and they find these objects in the cave. Actually, these objects are found over a long period of time by different people, but this is a nice story. And these are these boys after they grew up. So you can see that perhaps they're not the most reliable people, but anyway, that's an interesting part of the story. So, and these gentlemen or boys didn't know what to do with these objects after they found them. So they took them to an art dealer in Bethlehem. And remember, at this time, this is a time of political change in the Middle East. So Israel is being established, the Arabs are still there, and there's a lot of conflict. So this gentleman, he is an Arab art dealer in Bethlehem. And so he acquires these objects from these little boys. He hides them in his store for a while. And then eventually he decides that maybe he can sell them. You can imagine an art dealer doing this today. They have some interesting objects. They want to sell them. I saw some in Budapest last week. Somebody asked me, can you date these? So he didn't know what to do. At this time, there's no radiocarbon dating. So he went to see his friend, which is this gentleman here, who you can see is a very important guy because he has a lot of robes. And he is the Syrian Archbishop of Jerusalem. So this branch of the Catholic Church in the Middle East. And so he acquired these objects, and he said these are very important, and they should be kept safely. And so you can see we're getting away from science at the moment. So the Metropolitan Samuel, this gentleman, the Archbishop, after a while his church is needing some money. So he did what everybody does when they want to raise money. He went on a trip to the United States. So this is what he did. This is in the 1950s. And he gave a lot of talks about these objects. And he also decided to sell them. And so the way he decided to sell them is very interesting. So I think that since you are English students, you can read this advertisement. This is an advertisement in the Wall Street Journal, which, if you know anything about American newspapers, you know is a kind of business newspaper. It's for the stockbroker to read the reports. And it says, biblical manuscripts, almost 200 BC, for sale to an educational or religious institution. And so the Archbishop had one concern, which was that he shouldn't sell them to the Israelis. He wanted to sell them to somebody. He didn't like the Israelis because he's an Arab. And so he wanted to sell them to somebody else. But unfortunately, the people who bought these objects actually are working for the Israelis. So now these objects are in the Israeli museum. So, and this is a very modern museum, but it's built as a result of this. But there are many other examples of these objects, and I just wanted to review briefly this little story because it's kind of different from the rest of my presentation. So the date of this object, I just show you as an example. This is measured in Arizona and also in Zurich. There's another lab there. And the ages are the same. And this is the age based on the radiocarbon age. That is the measurement without doing any calibration. And then this is the estimate using a calibration, which is the same as what somebody would tell you the age of this object was from the style of the writing. So I'll show you a few other objects. Maybe I move a little more quickly. This one is called a Vinland map. So this was a controversial object in the Americas because it is supposed to show the New World, that is America. Parts of it are here, Greenland and Newfoundland. Before, this is supposed to be older than Columbus. So until sometime in the 1950s, it was thought that Christopher Columbus discovered America. Of course, now we know this is not true, that actually lots of people discovered America before that. And obviously there are people already living there, so this was just a mythology from this time period. And this object is also made on papyrus, on parchment. And it turns out to date from about the 15th century, so 1400 and something. So sometime just before Columbus is sailing to the New World. So this fits with the story that maybe he got some information. He's not just sailing across the ocean without knowing anything. He actually knows that there is something on the other side. And of course, since then, we know that there was a lot of information available to people in 1490 about the New World. So I have a couple of other examples. I move a little bit more quickly. This one is a papyrus. This is from an ancient text called the Gospel of Judas, which dates from about 200 or 300 AD. So at this time, there are many such manuscripts floating around the world. Many of them were destroyed, but some of them have survived. And so, again, shows you the importance of being able to take a very small part of the material to do the dating, which we can do with the accelerator, which wasn't possible previously. I'll show you one, maybe two more examples. Okay, so this is for the really English scholar. So another object which attracted a lot of interest recently in the last few years, actually for a long time, was an object which is a book. It's called a Voynich manuscript, and this book is made in a language that nobody understands. Zero. Nobody in the whole world understands this language. And so this object is known from sometime in the 1500s, and you can read this part. This part is in Old English, so it's harder to understand, even for me. And this book is very strange. So it has funny writing in it, but nobody can understand this writing. It's not Hungarian, it's not anything. So it's written in some kind of code, and I don't know if I can show a picture of what it looks like. So this is what the writing looks like, and everybody looks at this writing and says, it looks a little bit like something that we recognize, but actually it's not. And so this object dates to about 1430, so similar time to this other map that I just showed you. And many people tried to decipher this. The computer systems of the US government were used to try to decode this object, and they couldn't do it. So if you can imagine that the National Security Agency and all these people don't know how to decode this object, it must be very difficult to decode. And so really nobody knows what this book was for, because it has strange pictures of, it looks like plants, looks like astronomy, looks like some kind of rituals, so bathing or something, and so nobody knows what it means. And everybody, it's like the Shroud of Turin. If you go on the internet and look at this for this object, and you just Google this object, you will see people who spend their entire life trying to understand this book. I don't suggest that you do that. I think there are better things to do. So I'll try to get to the end of my talk. So another thing that happens to me because we do radiocarbon dating is somebody comes with a famous painting. This is one that they dated in Tucson. They didn't like the results, so they came to Debrecen. It's quite interesting that they did that. And in both cases, the results are the same. And if you look at this picture, it's supposed to be from Raphael, which is about 1500, 1510. But if you look in the paintings of Raphael, there is no painting of Raphael that looks like this, exactly. So it's dating for 200 years later or so. So this means probably somebody copied the painting. And I talked to lots of people about these questions, and they say, well, how can that be? And I said, all you have to do is to go to an art gallery, and you will see that there are students sitting there copying a famous painting just to learn how well they can paint, to learn the art better. And so these paintings probably end up somewhere. I show a couple of other examples. This is an old Egyptian manuscript. It's called the Book of the Dead. It's from 1500 BC. So this is the Middle Kingdom of Egypt. So this is just to show you some other kinds of objects that we can date. This is my favorite object because it's a duck. It looks like a duck, so it's a duck. That's an English joke. So somebody said that once. If it looks like a duck, anyway. So, and this is a duck decoy. It's found in a cave in Nevada where there's a whole cave full of duck decoys, really. And they all look like this. And so the Native Americans at the time, I guess, liked to hunt ducks. And so they build the decoy. They can hunt the duck the same way, convince the duck there's another duck here, and they can sneak up on the duck. So these ones I skip over. So we can date other kinds of objects. And so I just try to finish up. I'll show you a few other pictures just to show you that we don't spend all the time in the lab. We don't just wait for the person to bring us artworks. We also do other kinds of science. We do geology and archaeology. And so I have some nice pictures. This is an easy, very easy part. These are taken in the Qinghai province, which is in the northern part of the Tibetan plateau in China. And so these are just some nice pictures to show some of my colleagues sampling, in this case, lake water and river water for carbon-14. So they're interested in looking at how old the water is coming into the lake. There's some geological processes that are going on in the lake, and so on. And so these are really just nice pictures to show. So anyway, you have to be in the airport and eat food and meet the local people. And these are some wildlife in the area. This is called a yak. I guess in Hungarian it's the same. So, and let me see. And so anyway, the point of my talk is to say that for me this is a lot of fun. So we use science, but we apply it to very interesting things that average scientist doesn't apply them to. The average scientist is working on some subject that's very difficult to explain to other people, but science can also be applied to things like art. It can be applied to lots of subjects where maybe it's easier to explain, but also it also has a wide application. And so I guess the conclusion of my talk is to say that if you become interested in science, there are lots of things you can do. You don't just have to work in a lab on measuring some very strange property of some material that nobody else wants to know about. You can do something that's interesting. You can also go to exotic places And so if you have any interest in science, I encourage you to develop that interest. And so finally, I'd like to say Köszönöm szépen to my host. And I have a final picture here, which is a very large meteorite. That's a whole other talk, but I won't give it today. So thank you very much. Köszönöm szépen.